Okay people, today we're going to do some work and let's start from some fundamental basic ideas, and this fundamental basic idea is really something you have done before, and let's see how good your secondary school knowledge is. First question of the day is, what's the definition of work done? Capacity to do work, but what's the formula, what's the definition?
F times
F times D, okay, good. So F times D. So, are you sure that's the complete definition of work done? That's force times displacement or force times distance. Is it force times displacement or force times distance? Is it distance or displacement? So you say distance. How many of you say that it's distance? Okay. How many of you say that it is displacement? Okay. So those of you who choose distance, you must be careful to say that. You must be careful to know that that means direction doesn't matter. Now let's take a look and see whether direction matters. If I were to have two objects, I pull it with a force F, same mass, I pull it with a force F over here, which object is going to travel faster at the end of the same journey? B is going to travel faster, right? So obviously, the work done in B is bigger than the work done in A. Now, what does this tell us? It tells us that actually the direction of motion, the relative direction between the force and the displacement matters. So when direction matters, it is definitely not it is displacement. Okay? And it's not just any displacement, because over here the displacement is here, over here the displacement is here. The force is the same, the displacement is the same. So if we just take the same force times the same displacement, then it should be the same one. So there's something that is the angular component that we haven't taken into account. Yeah? So over here I'm going to introduce to you this idea that it is actually not just F times D, it is actually force multiplied by the product of force and displacement, not just any displacement, but displacement in the direction of the force. Yes, correct. Exactly. This is where students will miss out. No problem, I can tell you. Year in, year out, no issue with force and displacement. It is the direction, in the direction of the force. That's the most important part. And that's the part that makes the difference between O level and A level. Because in O levels, you'll always deal with this. You never deal with this. You never deal with this concentration. Okay? So I'm going to show you slowly how this definition is going to lead on to something else over here. Okay? Now let's take the easy version out and let's focus on the more difficult version. Yeah? Displacement is a vector. So therefore, if I were to resolve the displacement into two ways, in two directions, there are two ways I can do it. And you tell me which one is the correct one. This one F, this one D. So I break D down into this one and D1 and D2. So this is vector D. Or F over here and then D over here, D parallel and D perpendicular. So there are two ways of resolving D. One, basically I take this, this is not the one. Salah. It should be this one plus this one. So first case, I take this one plus this one gives me this vector. Second one, this vector plus this vector gives me this vector. Two ways of resolving. Which one is correct? How many of you say that one is correct? This is one, this is two. How many of you say number two is correct? Okay, 1, 2, 3, 4. Okay, good. I don't know, is that a twitch or? Okay, most of you say that it's 2, and that's correct. And let's know why is it correct. Yeah, it's correct, but we must know why it's correct. First of all, the vector that you resolve must be the hypotenuse. Must be the hypotenuse, yeah? So that's the first thing. Second thing you must check is that the two components that you resolve must be at 90 degrees. Okay? So this one failed on two accounts. This is not the hypotenuse, and this are not perpendicular to each other. Okay? So it fails on two accounts, so this is wrong. So it's this one. Now let's take a look. The displacement in the direction of force, is it D parallel or is it D perpendicular? Is it D parallel or is it D perpendicular? The force, the displacement in the direction of the force. D parallel, because the displacement in the direction of the force. So if this is theta, can you see that D parallel is actually equals to D cosine theta? This is the adjacent, this is the hypotenuse, so it is cosine. So that full formula for work done is this one. Now please don't just remember the formula as FD cos theta, because Mr. Terence Chew, if Mr. Terence Chew would set a question, I'll definitely be nasty enough to give you a situation that looks like this. I'm going to give you 60 degrees. And you know what? A lot of students are going to go 60 degrees as angle theta, which is wrong. What should you put? Yes, correct, 30 degrees. So you shouldn't just remember the formula, you must remember to tag the angle to the correct angle. So how will you describe angle? It is the angle between the
direction and the force.
The angle between the what and what vector? Come on, it's not like a rocket science question. It's the angle between the two vectors. Which are the two vectors? There are only two quantities over here. The force vector and the displacement vector, exactly. Have you learned dot product? Cross product, dot product? You haven't learned. Okay. In the future, if you have learned dot product, cross product, I will explain to you why is it that the product of two vectors can give you a scalar quantity. Yeah? Yes.
Is there anything wrong with doing F cosine theta times B?
Excellent point. There's another way that you can resolve. Yeah, you can resolve the force in the direction of this is force times cos theta, and this is force times sine theta. So you're resolving the force in the direction of the displacement. Can, no problem. The reason why I did what I did was because I'm trying to follow as close as possible the definition. Because if I show this, then you start getting a little bit confused where is the displacement in the direction of force. Kind of thing. So you are absolutely fine if you do resolve the force in the direction of the displacement. And so either way, it is okay. Now let me show you another example. Since you mentioned this, let me digress a bit and show you another one which is this, which I can use two methods to look at displacement and the force. Now take a look at this situation. You know moments, right? It is not in IB syllabus, unfortunately, which I think it should be. This is D. So you've got theta over here, and you've got this situation over here. The moment created by this force is it FD? It cannot be FD because it cannot create the same moment as a situation like this. Right? It cannot be FD. Because if it is FD, then this moment will be the same as this moment. Obviously not. Which one has a bigger moment? By your gut feel. First one or second one? Second one, obviously. So the first one, the moment is actually due to two components. You can resolve the force. F, this is sine theta. This is F cosine theta. What's the moment created by this force? Excellent. So therefore the moment is Fd sine theta. That's one way of looking at it. The other way of looking at it is actually to look at the perpendicular distance, which is actually this one. This is actually the perpendicular distance, not D. So if you look at the perpendicular distance, it is actually D sine theta. So you can take D sine theta times F or F sine theta times D. Either way works out. Okay? So it's something similar to what we did just now. You resolve the displacement to the force, or you resolve the force to the displacement. Either way works. Cool. Okay, good. So let's move on to talk about three special situations. Anything in between are the general. So what are the three situations? The first situation is theta equals to 0 degrees. That will give you your usual thing that you did in your O-level syllabus. Cos 0 is 1. Next special situation. Theta equals to 180 degrees. So work done equals to Fd cos 180 degrees. And what is cos 180 degrees? Negative 1, exactly. So now here comes the problem. Work done, is it a vector or scalar quantity?
No, it's a scalar.
Energy, is it vector or scalar? Have you ever heard 5 joules in the north direction?
That's because two vectors multiply, right?
That's the point. There's actually two ways to multiply two vectors. It's not called dot product and cross product. One gives scalar, one gives vector. So in this case, it's dot product. So because it results in energy, therefore it is definitely a scalar quantity. Okay? Now here comes the dilemma. If it is scalar quantity, why negative sign? Why is there a negative sign if there is a scalar? I mean, the usual thing that you deal with is velocity and acceleration, right? There's negative acceleration, there's negative velocity, there's negative displacement. All of them are vectors. So therefore, if you have a negative over here, why is it still a scalar? Yes, correct. So what happens is that the force is here, but the displacement is here. I will talk about what sort of situations you have where you can actually have this kind of situation. But first of all, what does it mean when you apply a force and the object moves this way? Why? What does it mean to have a negative work done? Let's take a look at the scenario. If you have a car moving in this direction, you jam brake. What's the frictional force? Yeah? Okay, so this is the situation now, car jam brake. Now what happens to the KE? It goes down, right? So the negative work done simply means a decrease in energy. It is not direction. When you do negative work, it means that you decrease the energy. Yeah. Let's take, for example, another situation where you do negative work. Let me try to draw a very good drawing. If you wonder this is what this is not a banana, this is a hand.
The predator one.
Is it okay, so you have a box over here, yeah? And the force you apply, okay, say for example you apply, in order to hold the box there, you have to apply a force there, right? And what if I were to lower the object down? Okay, so the displacement is down. Can you see that this is the case over here? What happens to the GPE? Decrease, exactly. So that's why it is a negative work done. Positive work done, that case over there will be when I push it up. The force that I exert is up and the displacement is down. Okay? You like
So, but,
yes.
but when you're lowering it down until like accelerating it down.
Ah, okay, that's an excellent point. So I'm considering the case where I'm already moving at constant velocity. Yeah. Constant velocity. So the KE remains constant. Yeah. Yeah, that's why there's a negative F, because if you have this situation, it is positive F. But how do we represent a force that is opposite? So that's where the negative, the cosine results in the negative, yeah. But what I'm concerned with is you must understand the negative sign as a decrease. What's the significance of it? Yeah, it's not a vector quantity, it's because it represents a decrease in energy. Okay? Now, the next case I'm going to go through is also a mind-boggling case, which is make a guess, people. You've got 0 and you've got 180 degrees. What do you think is the next case? 360. 360 is 0. 90, excellent, 90. So theta equals to 90 degrees. You've got a case where you have a force up here and you've got the displacement here. How on earth does this happen? So say for example, I got a pen over here. I wish I got an apple, but anyway. So I got a pen over here, and then I move the object this way at a constant velocity. Do you agree that the force I exert on the pen is upwards and the displacement is forward at a constant velocity? So let's take a look at FD cos 90. What is FD cos 90? 0. Excellent. So ask yourself, if I were to move at constant velocity, is there any increase in or decrease in K? If I were to move like this, is there any change in GP? So GPE 0, GP change 0, K change 0, and that's why the work done is a big fat 0. There's no change in energy. Okay? So whenever you want to find whether work is done, you have to understand whether is there any change in energy. If there's no change in energy, no work done. Now here comes the dilemma. If I ask you to hold a 10 kg dumbbell like this, you obviously sweat right after 1 minute. Agree or not? Hello? Am I correct? Just hold it. Now if you hold a dumbbell like this, do you do any work?
Yes. No.
Do you have any displacement?
No.
If you exert a lot of force but no displacement, right? So why do you sweat?
Because you're trying to maintain a
Sorry?
You're trying to opposite moment, like.
But you don't have any displacement by definition if you have 0 displacement. No matter you exert the force of a Superman, also knows no work done. But you sweat. You know that you are actually doing work. You are burning food, I'm sure. So how do you reconcile this? Okay, correct me biologically. Am I right to say that whenever you need to exert the force, there's a lot of biological processes happening here? Yeah, you need to convert chemicals and then therefore it causes a contraction. So actually a lot of energy conversion is happening. But the problem is that this energy conversion doesn't get converted into an actual mechanical energy like GPE or KE. So what happened is that the work done is 0 doesn't mean that there is no energy conversion. So all the energy conversion is to heat. I don't think that there's sound unless you're screaming. Yeah? So the thing is that there's a lot of energy conversion, but there's no work, no effective work done. There's a lot of energy conversion, all of it is to waste energy. There is no useful work done. Get the subtle idea? So you need to be very careful when you say work done. When I have no work done, it doesn't mean that there's no energy conversion. I can actually do a lot of so-called work, but there's no useful work out of it. And for that, we define it as no work done. Yeah, it's just like almost like you worry, and then your head turns white, and then nothing's get done. You do a lot of work, but there's nothing done. Okay? There's a lot of conversion of energy, but there's nothing useful that comes out of it. So whenever we come back to this definition of work done that I wrote just now, we are focusing on useful work. Meaning either change in GPE or change in KE. So much of ideas. Let's focus on two energies that you're very used to. Which are the two forms of energy that I've been talking about? Let me hear it. There are two forms of energy. I mentioned it just now. Kinetic energy. Yeah, let's start off with the easier one. Okay? So if I have a block over here, I move it through height h, and then the force that I apply, the minimum force I need to apply must be, if the mass is m, what's the minimum force I need to apply so they can travel outwards?
mg plus 1.
Oh yeah.
What if it is already traveling? I just move it at constant speed. Mg, right? So, can you agree with me that the work done is equals to mgh? Cos 0. So that's why it's mgh. Now sometimes we say that this is actually GPE. Now this is where things get a little bit of issue. Let me show you why is there an issue. Let's consider three levels, A, B, and C. Each of them 1 meter. If I move this block over here, block X and block Y over here, if I move this block from A to B, and each of them has a mass of 1 kg, 1 kg. Let's take G to be 10, yeah? So do you agree that the work done, which is mgh, which is equals to 1 times 1 times 10, which is going to be equals to 10 joules. But the same thing, if I bring it from here to here, the work done is going to be 1 times 1 times 10, which is 10 joules. So therefore, I can conclude that the GPE over here is 10 joules and the GPE over here is 10 joules. Can you see the fallacy now? How can I have two levels at different height to have the same GPE? You see the logical fallacy over here? Yeah. So how do I reconcile this? Is this gravitational potential energy? Or is it not? Yeah. Yes, obviously it is not. But what it is over here is the change. It's a very important thing. Conceptually it is big. Although equation 1 is not very big. It's just a change. So you must be very mindful that delta GPE is change. Now, have patience. Later on in the year, you're going to learn the actual expression for the actual GPE at the point. So you will learn the expression, yeah? Together alongside with things that will enable you to analyze orbital motion and satellites. So be very careful. If you say it out, it's change in GPE. Now the next thing I'm going to do is I'm going to show you how you can get the expression for. Actually, I don't want you to do it yourself. So if I apply a force, it moves through a distance s. The expression for work done is going to be equals to F times s. Make sense? Therefore, this is m times a times s. Still okay? Now, still remember v squared equals to u squared plus 2as. If I start from u equals to 0, do you agree that as is equals to half v squared? Okay. Plong it back into here, this will give you half mv squared. So that's how it comes about. In secondary school, they couldn't show, the teachers couldn't show it to you because you haven't learned this.
So I thought it's EK equals to B squared over 2n.
Oh, okay, that one another way. There's another formula for that. Oh man. Yes, you're correct. EK is also equals to B squared. But for most of the cases that we're going to handle over here, that's exceptionally useful in particle physics. Yeah. We'll come to that. Have patience. Yeah. So let's try questions and let's get things done to concretize your knowledge. Can I assume that you know the conservation of energy? Can I have someone to confirm that by just saying it out. Today is Thursday. Anyone's name starting with a T other than Terrence? Sorry?
My name starts with N.
Although N and T a little bit far away. Anyone's name starting with T? Any Tan?
Shannon Tan.
Ah, yes, thank you. Tan. Come on. Conservation of energy states that, the principle of conservation of energy states that. No, Einstein is not going to be very happy on that. He said in the actual words, I mean, they might be missing a word or two, that total energy cannot be or destroyed, but it can be converted from one form to another form. Yes, so that's basically. Now I'm going to show you one very important idea in equation form. Then I'm going to show you equations, questions like this, which means that any work that I do must result in change in energy, which must result in a change in your context, change in GPE or change in KE. But I'm going to add in something else, which is work done against friction. So any work that you do needs to go through this, or this, or this, or all three of them. So in perfectly frictionless situation, you just need to cover this. If there's no change in height, you cover this. If there's no change in speed, you cover this. Okay? So I think this is the most broadest way to look at energy conversion. So let's start off with a simple question. Come on, if you don't know this, I'll be really, really saddened by it. I dropped a mass from 5 meters high, and then it falls down. Find the speed of the object. Seriously, I hope you find it insulting. Yeah, I hope you find it insulting. Come on, entertain me. Yeah, use 9.81. Since you're using calculator, use 9.81. So this is the warm-up phase. Yeah, warm-up phase. So half mv squared equals to mgh. That's right. How? 9.9. I'm going to show you how you can use that. So the work done by external force, is there any other forces other than gravitational force? No, right? So therefore this is 0. This takes care of the gravitational force already. So any frictional force I mentioned? Is there frictional force? I didn't mention air resistance. So let me show you how you can use this one. So 0 equals to GPE final minus GPE initial plus KE final minus KE initial plus work done against friction, which is 0. So KE initial is 0. Agree? Yeah. So for this one, because it is a change in GPE, we can actually take reference one of the level as 0. Let's take this reference level to be 0. It doesn't matter because it is a change. So therefore, GPE final is 0. Therefore, eventually you get 0 equals to minus GPE initial plus KE final. And that's it. So therefore, KE final equals to GPE initial. Troublesome as it may seem, but this will become exceptionally useful when you have multiple energies coming in. It provides a system. I'm going to give you an example later on that shows you how this can be more useful than just simply writing half mv squared equals to mgh. It'll come soon. 2 examples later. Let's move on to the more difficult example. It's literally going to be an uphill class. F equals to 120 newtons. This is 10 kg. There's a frictional force of equals to 20 newtons. Okay, fine. And you move it over a distance of 8 meters. Find the GPE gain. Find the work done by the force, the 120 newton force. Find the work done by the friction, and hence find the velocity of the object. Be very, very careful of whatever you substitute inside the equation. This question is designed for certain things. I leave it to you to find out yourself.
So it's useful work done, right?
It's always useful. Like, you mean which one? This one or this one?
What to?
This one is by this force, so it's useful. It may not be useful, it's just work done by that force. In fact, useful work should be work done by that force minus the work done by friction. So GPE, that's very easy. GPE is just equals to the mass of object 10 times 9.81 times 8, right? Times 8.
8 no sir, 8 sine 30. Yeah, it's 8 sine 30.
8 sine. Yes, correct. Be very careful about this. 8 sine 30 is a nice number. It's just 40 times 9.81. Someone shout out the number.
394.
392. Now, why do you use 8 sine 30? Let's go back to the concept. Yeah, let's go back to the concept. Because your weight is pointing vertical, therefore, I mean the height that you use must be the vertical height. So that's why it is 8 sine 30. Good. And then work done by the force. So work done by force should be equal to 120 times 8 sine 30 as well, right?
It's because the direction of force the same, right?
So it is not 8 sine 30, it is 8. So it is 960. Okay?
So what, it's useful work done, right?
No, useful work will be work done by work done, then minus weighted work done by friction. So it's just work done by the force. And work done by friction will therefore be equals to, we just take the positive number, so it will be 20 times 8, which is equals to 160 joules. And therefore, how do you put all these three numbers together to get your KE? And therefore your speed.
Change in energy equals to all that. So, you add everything.
Yep. Therefore, you get your. Okay. Now, before I stop recording it, before I just close this lesson, I have one parting question for you to think about. Okay? Copy whatever you need to copy over here first, and then I'm going to give you the parting question. And you think about how you're going to approach this problem. The question is this. You need to listen to probably wait for 1 minute so that you can finish the question. If this is bad drawing, it's supposed to be a flat surface. I'm sure it's flat. So need to tilt a bit. Okay, Ken, so let's take a look at this question. It's supposed to be a horizontal surface. All surfaces in this question is frictionless. Okay? Frictionless, huh? So when I release this, what will happen? When I release this, what will happen? Say if I give this 20 kgs. Things will move, right? You know, things will move, right? So how will things move in the end? Exactly. The mass will move and the ram will also move as well. So the question for you is, how do you find the velocities of the ram